Hello. Welcome to our sharing, and our sharing is about fuzzing. It is not about the exploit, okay? And firstly, let me introduce ourselves. This is me. My name is Juwei, and my Twitter account is PanicXNU, and I'm a senior staff engineer from Trend Micro. And I use this tool to find a lot of vulnerabilities and got several CVEs. And last year, I gave presentations in Black Hat EU and Code Blue Tokyo. And this is my colleague Junzhi.
Hello everyone, my name is Junzhi, and I am a worker at Trend Micro as an intern, and I do mobile security research, and I have found some fewer CVEs. Thank you.
Okay. This is today's agenda. In the first part, I will introduce what is the PanicXNU, and the second part is XNU version 1 to version 3. Actually, the version 1 is about the syscall fuzzing, which was the one I have presented in last year's Black Hat EU. And the PanicXNU version 2 is actually the LKit active fuzzing. The version 3 is about the passive fuzzing. Next part, my colleague Junzhi will introduce the fuzzing visualization and the daily operation. And the last part, if we have time, enough time, I will share you some very simple case study. Okay. Let me introduce what is PanicXNU. Actually, it is the XNU fuzzer. It now supports syscall fuzzer and LKit fuzzer. Maybe in the future we can extend the ability to support kernel extension and traps and so on. It is based on Google's famous fuzzer SYZ caller. You can see this picture. This page was created after my last year Black Hat talk, and the owner of this corner created this page. He mentioned that I has ported syscaller to support Apple's XNU. As you may know, syscaller supports Android, Linux, and even Windows, but it doesn't support macOS. And it also just do the syscall fuzzing. In this talk, I will share you about the PanicXNU version 3, which supports XNU fuzzing, include the syscall fuzzing and the LKit fuzzing. This is the architecture, fuzzing architecture. It is almost the same with SYZ corner. It has two components, the server side and the client side. Let me introduce the workflow. Step 1, the server side will start the client side, and step 2, the syntax engine or the generation engine will load the API patterns and the corpus DB. Then it will generate some syscall requests. And step 3, mutation engine also can mutate some parameters for this API calls. Step 4, API executor will receive these parameters and do the real request. After each syscall or LKit call, with the return value at step 7, it will check whether the return value has some heap memory disclosure. And at step 8, the API executor will also update the code coverage to the corpus DB. So this tool is based on code coverage driven. So I must add support for the code coverage in current XNU kernel. You can see this picture that I developed several sanitizers, especially the code coverage sanitizer in both the BSD subsystem and the LKit subsystem. In this talk, I think the most important thing is the code coverage support in LKit. Okay, before we dive into the later sessions, let me introduce two terms. The first one is pattern. The next one is corpus. Pattern is actually the API syntax description, and the corpus focuses on the parameters for the API. Okay, let me introduce the PanicXNU version 1. This is, as mentioned before, this is actually the one I already talked about at last year Black Hat EU. And you can simply say, you can take it as the syscaller for Apple XNU. And I wrote more than 500 API patterns, also as well as the several sanitizers, including the code coverage. And I use this tool find more than 50 syscall crashes, including 2 for the Pontoon macOS 10.14. I already talked about the version 1 in last year's presentation, and today I will give you 2 more trivial items. The first one is about how to add support for BSD code coverage, and the second one is how to enable kernel address sanitizer. Let's focus on the first question, how to add BSD code coverage into the current XNU source code. I developed a module named kcover, very similar to the one in Linux. And this module includes 2 major parts. The first part is the function sanitizer cover trace PC. This function is used to extract the code coverage data. And the second one is I registered itself as a kernel extension module to send back the code coverage data back to the user mode fuzzing tool. And in order to compare this module into the current XNU source code, we need to update some configuration files. For example, the master file, the files, the makefile.template. And let's see, this is an example how I register itself as a kernel extension module inside the OSF MK. It is very straightforward. I implement some functions like the kcover open, close, read, L control. And please pay attention here. I implement this kcover module inside OSF MK, not the BSD subsystem. So when you call the devfs make load, don't use the make dev macro, because it is different between the OSF MK subsystem and the BSD subsystem. You can see that the first parameter I use the hardcode value. And this, you can see the picture here. I already successfully inject our sanitizer cover trace PC function into some basic blocks. Now you can use genetic algorithm fuzzing to do the further fuzzing smoothly. Here has a very small problem that if we want to do some fuzzing visualization, it is not good with such kind instrumentation, because you can see that there are several blocks without the sanitizer cover trace PC instrumentation point. Question 2, how to enable KSAM? You may download the source code of XNU and compile it maybe in release mode, debug mode, and even KSAM mode. But if you try that in KSAM mode, you can get the output, the kernel bin output. But if you try to boot your machine with the KSAM kernel, you may find that it can't boot your machine. The root cause is that during the boot stage, some KSON stop functions will check the shadow memory, but the shadow memory is not initialized at that stage. So the workaround is as below. We can add the below functions into the KSON blacklist, blah, 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 such kind. Then compile it again. You can boot the KSON kernel successfully. Okay, this is PanicXNU version 2, LKit active fuzzing. I think this part is the most important part in today's talk, and I will describe it in details. It is also it is still based on syscaller, and so it is code coverage driven. In order to make it works, we must develop some API patterns for the LKit modules. But you may know that LKit modules, most of them are closed sourced, not open source. So we use the reverse engineering to extract some API patterns. Okay, in order to use the syscaller for fuzzing LKit modules, we must have LKit API patterns, and we must have the LKit API executor. And the most important thing is that we must have the module code coverage data. Or if you don't have the code coverage data, you are not smart, right? And as for the API patterns, we for the open source LKit modules, you can just extract the API patterns directly from the source code. But for those closed source LKit modules, we mainly use reverse engineering and other methods. Okay, let's see the LKit attack surface firstly. In current XNU, there are several subsystems. In this talk, we focus on the LKit subsystem. And inside the LKit subsystem, there are total 88 interfaces. And in the next session, in the following sections, we only take the LConnect method as an example. Okay, how to extract the LConnect method patterns? Because this interface is a very famous interface and is a very big attack surface. We can extract the API patterns. Maybe you can write a script to extract the patterns from the structural tables, the S method and S dispatch. But for those unstructured code, you can only use the reverse engineering to extract the API patterns. Okay, let's see the result. Currently, we already extracted some API patterns from a lot of the LKit modules. For example, the accelerate family, the LAVB family, and LHID family, and so on. Let's see an example, the Apple FDE key store. This is an example of this module. You can see that there are three main methods: SYZ open surface, SYZ core method, and SYZ close surface. The important one is the SYZ core method. After reverse engineering, we found there are 31 connectors for this module, and you can see the connector with value 1. It maps to the function user client close, and we get the information that all the parameters are 0. All these results are from reverse engineering. And so the reverse engineering seems very important, and our further depends on it heavily. So if we have some mistakes in the reverse engineering, the following generation or mutation fuzzing is totally wrong. So how to review if our reverse engineering is right? Okay, I have several methods. First one, don't depend on the reverse engineering. So we have the passive fuzzing and combine the passive and the active to make it not that important. And we can also, with the help of fuzzing visualization, to check if the reverse results are right. The second one, currently the actuator don't support LKit. So we must add support for the LKit call method. For example, I don't change any the original syscall API executor. I just assign the call name as well as the call method. And you can see if there's a fuzzing request, it will call the executor syscall. And since the call name is not empty, so the function inside the call name will be called directly, and the method is actually the SYZ call method. I implement this function in this project. Okay, let's focus on the most important thing: how to get the code coverage from those closed source LKit modules. There are maybe several methods, for example, DBI, SBI, or even inter-PT. But I don't find any existing solution or projects for the Mac OS or Apple's kernel. And I decided to use the SBI function to get the code coverage for the Apple's kernel. Especially for those closed source LKit modules. I got the SBI idea from the project PEBIL. Okay, let's see what it means. This is an example of Apple FDE key store. It is, now this picture describes some instructions before any SBI. You can see that the first instruction is push RBP, then move RBP, RSP, and so on. Let's see the result. After my SBI, you can see that the first instruction becomes a jump instruction. Just it seems that it is patched, and it directly jumped to another function. So what is the target function? You can see the target function like this. The target function seems almost the same with the previous original function, except that at each basic block, at the start of each basic block, it calls shellcode. The shellcode, you can implement whatever you want in the shellcode. In this talk, I just use the shellcode to extract the code coverage. Okay, so this is the main idea of our SBI. And you can this picture is an example of our one result. So what is the differences between the before SBI and the after SBI? You can see that before SBI, it only has one text section, but after SBI, it has two text segments. The left one in color brown is the original text segment, and the next, the right one in blue is my cloned SBI text segment. Okay. This is the differences. So let me introduce the details about how to do the SBI for the kernel macro, the macro files. There are three parts. First one, you must update the text section. And the second one is you must update the relocation. And the third part is that you must update the macro file structure. I think the first one is the most important. You must fix all the target instructions. And in our tool, we only focus on the instruction type, or memory, and or new. And for those instructions, we fix the jump table and fix the new jump and fix the operand value. For the second part, we must fix the local and external relocation. Okay. Just jump to the first part, update the text section. As mentioned before, for the original function ABC, I just patch it to let it jump to my new SBI function xxxxxx, and the new function is almost the same. It has the same 3 blocks, block 1, block 2, and block 3. The difference is that it calls the shell code y at the every start instruction of the 3 basic blocks. Okay, this is the SBI. And here is the full list of the instruction type. I get this list from the IDA scripts. And we only focus on the all memory type instruction and all new type instruction. Here is an example about how to fix the new jump and fix the operand value. For example, the left picture is the source code of the binary view of Apple FD key store before SBI. You can see the last instruction, JBE short local 3B18. Let's take it as an example. We must fix the operand D2 to C4. This is because we add so many instruction points, the call shell code at each basic blocks. So we must fix the relative jump. If not, it will jump to the wrong address, right? So we must fix the operand value. And we also must fix the new jump to far jump. This is because it is the same reason, because we add the instrumentation points, so it may jump outside the original scope, because the short jump can only jump to within FF scope, byte scope, right? And this is a list in our tool that we replace all the short jumps to the long jumps. Another question is about the jump table. You may see that in Apple's macro, that you can always see some jump tables. Jump table is the data in text. It is very special. In our SBI, we must recognize it as data instead of text, or everything will run. And after recognize it, we must fix it, because every entry in the jump table points to the original text code branches. We must fix it to let it jump to our new SBI text code branches. Okay, how to recognize it? I have a workaround. First, you can check the first instruction, LEAXJPT-3EF7. This instruction is of type O new, and then we can check the table, the target address, JPT-3EF7. It locates inside the text section, but it doesn't belong to any basic block. Then we check every entries inside this jump table to see if all of the entries jumps to the existing basic blocks. If yes, we take it as a jump table. Okay, how to recognize it? And how to fix it during the SBI? It is very simple. Just update the value of these jump table entries to make it points to the new code branch in the SBI text. So this is how we fix it. Just update the entries. Okay, the next part about the relocation. Firstly, what is the relocation? You can see an example here. In the ADA view, we can see there's an instruction call L3. But if you open the FFD key store module with the hex in hex mode, you can see that the opcode is E8, but the operand value is 0. So how ADA or the system knows here is L3. It's simple because the relocation tables records here that as the file offset 1861, it is the symbol L3. So here comes another question for us for the SBI. Since we cloned the original text section, we must add the relocation entries or update the original entries to let the system know that our call L3 not call 0, right? So just update the entries inside the local relocation table and both the local relocation table and the external relocation table to make it works right, make it works well. Okay, the final part is update the macro file structure. We need to add the SBI text section and SBI data section, and we also need to add the shell code to do whatever you want. And for the existing macro header, you must update the watcher address and the watcher address. For example, the node command sim table, node command data encode, and such kind. Okay, this is an example of what we did for an macro, for an LKit macro. I added two segments. The first one is a text segment, and the second one is a data segment. And the name of the text segment you can see is text 00 panic all. Okay. As for adding the shell code, we must use the assembly code to implement your task. So in my idea, we just use we use the assembly code to just implement the simple task, just call an external function, and you can implement the external function in a standalone kernel extension driver. So you can use the C language to implement whatever you want. So this is the SBI summary. You must fix or not, fix the old memory and old new instructions, and fix the relocations, and fix the file structure. And you need to add the shell code to record the return addresses. And add two segments, the SBI text and SBI data. Here is another question, where to add these two segments. You can see that I add the two SBI segments before the node command link edit. So can we put the two segments at the end of the node command, at the end of the macro file after the link edit? My answer here, if you want to do an SBI against a user mode macro file, yes. But if you want to do SBI against a kernel mode macro file, the answer is no. Because if you do so, the system can't boot. Let's see why. During the initialization, link edit node command can be updated to a smaller size. What does it mean? The system module loader can do some optimization for the link edit node command, because inside the link edit segment, it mainly contains some strings or code signs. For example, code sign is a must during the check stage, but it is not a must for the module itself run inside in the kernel. So the kernel will do some optimization to make the kernel memory allocation smaller. You can see this picture. This is an example. If we add the SBI text or the SBI data at the end of this macro file after the link edit, the kernel, when it is loaded into the kernel will recalculate the virtual size, the memory size for this module. The result is 0x4800. It is not 0x5000. But the kernel loader still put our SBI text at offset 0x3000. So absolutely it will panic because it exists the allocated memory. That's why we can't put these two SBI sections after the before the link edit node command. Okay, there's some small limitations for the SBI project. It doesn't support FAT macro, but now it doesn't. It is not a big problem, and it doesn't support 32-bit macro, and the macro headmaster have free space for two more node commands: the SBI text and SBI data. Okay, and the jump table identification is not a perfect solution, but it works well. Let's see a result for current status of our SBI. Almost almost all the modules we have the API patterns can work well now. Okay, if you use our SBI tool to failure boot your machine, don't reinstall your OS. Just use the following steps to recover your system. Okay, in the secure recover mode. Okay, next the final one is the PanicXNU tool version 3. It is about the allocated passive fuzzing. Here, the passive fuzzing, I mean, it is not the one you see in common scenarios. I don't use the hooks to maybe the passive fuzzing you understand is about use hooks to mutate the parameters during normal function call. I only use the hooks to dump the parameters into the MySQL and the MongoDB, and I convert this data into the corpus DB to let our tool consume directly. Okay, let's see the result. I use this tool, the hooks, to get a lot of the allocated connection open data, and also get a lot of the allocated connection data, and also get a lot of the real data, the data into the MongoDB. And finally, we have all the API method parameters. Then we need to convert this data to the corpus DB. And you may know that syscall uses a concept program to fuzz instead of single API fuzz. Program is actually a sequence of API calls. You can see this picture as an example. It calls the socket and then use the return value as the first parameter for the bind API. So it has the concept program. I think the advantage of this fuzzing mode is that it can solve some context problem, right? And I also use this concept to do the my passive fuzzing. I record a sequence of API calls. For example, the last one, the length is 3. So I record three API call and put them together. The first one is P0, the second one is P1, the third one is P2. The value of this, the value is actually the MD5 hash value for each single API call. And then I compare them together to produce the programs. You can see it as the picture as an example. The program shows that we firstly use SYC open surface to open some alkyd surface, and then calls the SYC call method to fuzz some to call some alkyd method. So it can partially solve some context problem, right? Okay, next is the alkyd fuzz summary. We can compare the active and the passive alkyd fuzz now, because we have the alkyd open and the call syntax description by the reverse engineering, and we have the passive sequence corpus by hooks, and we also have the code coverage of closed source alkyd modules now. So we can extend the ability of syscaller to support fuzzing alkyd. The combination advantages here, I think the passive corpus can be used to fuzz system alone. It doesn't need the active API pattern developed by the researchers. So it can make us don't rely on the reverse engineering so heavily. And the passive corpus can help review if the active patterns, API patterns are correct. And the passive corpus gives the chances that even the patterns are wrong, we can still fuzz in the right direction based on the genetic algorithm. This is the alkyd fuzzing architecture. We use some client hooks to get the passive API sequence corpus. And we can also use the SBI tool to get the code coverage from the closed source modules, alkyd modules. And we also have the dashboard to see what happens in everyday fuzzing. So next, let me invite my colleague Junzhi to give you an introduction of the fuzzing visualization under the daily operation.
Here we go. This is about fuzzing visualization, and coverage is first the class netizen in our fuzzing. This is our passive fuzz. We just hook mainly about two main functions: is alkyd service open and alkyd connect core method. We will have a demo video. Okay, this is our dashboard. You'll see we have 10 one XYZ manager and 10 XYZ father running on VMware Fusion. And the next one is our daily earning. You can see we have run nearly 6 million programs until now, and this number keeps growing. This is the most exciting part. It's our CVE machine. You can see that it produces about 1 panic a day and keeps users away. Every day we got panic. And next is passive fuzzing framework. We just see. You say that it's and fuzzing signals. Fuzzing signals is internal representation of code coverage. You can see that after restart, the coverage keeps growing. Signal numbers. Corpus means that we have about nearly 2,000 programs. And this is our coverage data. We will choose a module. Most complicated accelerate assembly is about 3D acceleration. It's a lighthouse integration. Actually, we have a heat map for every function code coverage. And we have also lighthouse integration. I will show you in other demo. Lighthouse is a great tool for coverage visualization. We load coverage data, and it will plot for us similar heat map. And you can click from you can see that blue one is a heated block. You can even see in the compare mode that will be very friendly for coverage review. Another one is that diffing tool. We know that after update for programmer, they fix all the bugs and you introduce some new features and new API. For security researcher, we do some diff so that we can find all the ND. And we do some diff to find new bugs and new attack surface. How you can see it's a changelog from high Sierra to macOS module. In kernel, it has opened 2 syscalls and 1 mactrap, and some new routines in subsystems. And most importantly, you can see that it has added 3 MIG subsystems and contains hundreds of routines. So how do we do that? We are collecting binaries from different machines, and we have rules in Tomo language. And we also write a script in Ada to pass in this binary and rules so that we can produce different JSON files. by diffing these JSON tools, we can get what has been changed in these different versions. Another demo. Yeah, we choose a module, and this is worth kernel and different versions. Hasira and Mojave. Yeah, you can see we have added some. This is a simple JSON patch, and we can see we have yellow are changed one, and the green are new one. Oh. Yeah, and it's our daily fuzzing operation. So we are not just developing this just to see a lot of charts and pictures. We are aiming at coverage more code and more attack surface. After some reverse engineering, we will modify our API syntax for fuzz and run it again, and we will add some text for our fuzzy environment. Here is a demo. From this flowchart in IDA, you will see most of our code was not in blue, which means that they are not hated at all. So why? It has two limitations. First, it will check our entitlement, and second, it will check our boot arguments. So there should be some text to make it run. Yeah. First, maybe we can add some entitlements, but in fact, this entitlement is Apple's private, so we couldn't. And second, we can change the boot arguments. In fact, that's what really works. And other code block in DAC, and now they are hated. Next is the case study.
Okay. Next, I will introduce some very quick case study. The vulnerabilities found by this tool. This is 4435. It is a heap memory disclosure vulnerability. You can see that as the location 1.a, it caused as a shell init, and inside the shell init at location 2.a, it will allocate some structure memory without the mem set. So the memory may contain some garbage memory. And at location 1.b, the structure memory is copied back to the user mode. So what I want to show you is that the structure is like this. You can see that the offset 0x28, it only has the length 2 bytes, but in the source code, it only at offset 0x28, it only be mem set with 0 with 2 bytes. Remains the next 2 bytes unmodified. So the next 2 bytes start at offset 0x2a is copied back to the user mode. So it is not exploitable, but it may, but it can show a pattern here that the kernel structure memory, if it is allocated without mem set, without clear, and not all bytes are filled. For example, especially the padding bytes are not filled. Then the structure memory is copied back to the user mode. I think it can be a pattern. You can use this kind of pattern to search the XNU source code. You can use some search engines to search it. And I found several cases. One of them is like that. At location 1.A, the max count here is 17, but at at location 1.B, the count is 11. The count can be 11. And as this picture that the macro port info extension count is 17. So what happens? The structure, you can see this structure that under some condition that the reversed with field with 6 count is not filled, and the memory is copied back to the user mode. Then you can get 24 bytes disclosure, right? And this case was fixed by Apple internally before my submission, so there's no CVE. And there's another example, the 8529. It is a very simple OOR vulnerability that you can see that at location A, the RBX is controlled by the attack. It is a very easy vulnerability. Okay, so that's all for our presentation, and we want to credit the following people or projects: the SysCorner, the NetHorse, and to my interns, and one of my colleagues who helped provide the case on blacklist. Okay, that's all. Or if any question?
No hands for questions? Then I ask you all to give one more big round of applause for Juwei Lin and Junzhi Liu.